this one is the 15th edition of Force 2020 Zooms. And this is an impressive meeting with many people from different countries that love the language and are in a Facebook group together. Let me share the 50s. Where is the share button here? One moment. And this is the 50th edition of the Zoom group, of the Force 2020 Zoom edition. And then I want to say a lot of thanks to all our friends who were on the first meeting. You see on top one friend from Russia, people from Scandinavia, from England, from France. Here is Francois and Thomas from Germany, and Bernd, and many people from Europe, Italy, people from the Netherlands. Jos is here also in the meeting, and the people from USA, which of course are most of the Forders there. Here is Cornelius and our dear Dr. Ting. And here is Wilson is not more available on Facebook, and Don Golding and John Peters and Bill Ragsdale and Tom Zimmer and Michelle Jan from Canada. Abraham, we started the group with Abraham and with John Hardy here on Australia. Here's John Hardy. And Rob, also from Australia. Our friends from Taiwan, Qilu Shen, and our Shan, Dr. King, and I can't remember his name, but is somebody from the Novix group. From Chuck knows him very well. Dr. I can't remember his name, but a very dear friend from Taiwan. Here, the people from South America, Lázaro from Brazil, Álvaro, and myself. And here is Pablo Reda from Argentina. So all these people together started the first meeting. It was such a success that we arrived at this 50 edition today. So we have today in the meeting Bernd Ulmann. I don't know if Bernd is ready to present. We started a bit late.
He is. I am.
So the stage is yours, Bernd.
Thank you very much. I will keep things as short as possible. I would like to tell you a little bit about not only my passion, but maybe where my passion and Forth could get together. Let me share some of my windows. Where the heck are my... Okay, I will just, here. I would like to talk with you about analog computing. And what you see here is, first of all, a very simple analog computer. And on the bottom, you see the output of this very simple setup. And basically, I already talked a little bit about analog computing. Analog computing, that was a good topic, good discussion regarding artificial intelligence. As artificial intelligence is done nowadays, that's not really viable. As cool as it is building or even thinking about building a nuclear power plant next to your computer center, that's not really an option. At least it does not scale very well. And if we look at biology, biology solves these problems like in our brains, not algorithmically, but by interconnecting billions of neurons in a way that makes us unique. And so the logical question is, why not do this electronically? And the idea is old. Why not use physical concepts such as Kirchhoff's law to perform summation or to implement integration by charging a capacitor with a controlled current source and the like. And what you see here is a not so simple setup. The system used here is called the Analog Thing, and that is an educational small-scale analog computer that is at least powerful enough to implement things like the example shown here, that is an Hindmarsh-Rose neuron. That is a rather realistic mathematical model of the behavior of an actual neuron. And when you think of a neuron, you don't think of linear algebra, and you don't think of simple things like activation functions that look like sigmoids or the like. These are all things that we invented to make things easier for our computers. But when we want to build a real artificial intelligence, a general artificial intelligence that can honestly say, calculo ergo sum, I compute, therefore I am, then I'm really sure that it won't be a digital machine. It will be an analog machine. Of course, what I'm showing here is basically a classic analog computer. And what you see is a bunch of cables. And typically, the joke is not far from spaghetti code to this. But this is actually the program of the analog computer. You program such a machine by connecting various computing elements with each other. And what you see in the oscilloscope screen below took me hours yesterday to get my Mac to work again with my oscilloscope after I updated the operating system. Never update your operating systems when you have lots of open source and public domain software installed. It was really horrible. What you see in the picture below is the actual behavior of this simulated neuron. And the yellow trace shows the spiking and bursting behavior of that neuron. And the cool thing about this approach with analog computers is that it is basically a mathematical machine. A digital computer is a logical machine. You do everything with logic, with and nots and ors and whatever, and in an algorithmic way. Here you have nothing of this. It is a mathematical machine since it has summers, integrators, multipliers, coefficients, and you don't even think about programming in the way you do with an algorithmically programmed machine, but you think about programming from a purely mathematical perspective. And I will make the turnaround to Forth promised. What you see here is model of a neuron consisting of 3 coupled differential equations. And one of the beautiful things in an analog computer is I can, for example, change parameters. You see, I just changed this parameter and my neuron started to spike in a different way. Now it's outputting much longer bursts with much closer placed spikes. So it's more excited, or I can, for example, change the number of spikes in a single burst. I can actually play with the mathematical underlying system. And now things get really interesting. Programming analog computers with lots of wires is fun, but definitely not suitable for the 21st century. And I have something here to show you. You are among the first ones to see this actual machine. That is also an analog computer. It's too dark and the camera is really crappy. That is also an analog computer, but that is a very, very special kind of analog computer. Here, for example, you have a module containing 8 integrators. It's a laboratory prototype, as you can easily tell by the botch wires here. But the interesting thing about this machine is it does not have patch cables anymore. It's completely software defined. The computations are still done electronically with classic, more or less classic, there are some clever tricks, of course, with more or less classic analog electronics. Here, for example, you have coefficients. That's the coefficient board. That was one of the most complicated boards we ever routed. It has about 600 through-hole connections. It's really horrible. But the cool thing is when you can get rid of the patch cables, you have a fully software-defined analog computer. That's how it looks on the other camera. And that is just a proof of concept. The eventual system we are currently building contains many more computing elements than this. This was our laboratory prototype to basically test if it's feasible, if you can get enough precision to perform actual work on such a machine. And now comes the interesting part. You need, of course, some microcontroller to control all this. You need a microcontroller to send the configuration data to the analog computing blocks. You need the microcontroller to talk with some attached host computer via an Ethernet connection. And as of now, and I'm not that happy about this, as of now, the hybrid controller is programmed in C++. That is basic historic feature, if you will. But to be honest, the software is, in my opinion, too bloated, too complicated. It would be much, much easier to do something like this based on Forth. And you have several interesting problems in analog computers that you can't easily solve with C or C++. The problem is an analog computer is really fast. We are currently developing our own silicon, our own highly integrated analog computers on chip, and we expect solution times, well, much less than a microsecond. For certain differential equations, systems of differential equations, we are pretty confident that we can get solutions in about 200 nanoseconds, solving a system of coupled differential equations. And now it becomes interesting when you have a classic digital computer, for example, Linux system. Even if you write a kernel mode device driver, you need about 5 microseconds at least to answer an interrupt. That's ages for the attached analog computer. The analog computer is bored to death in these 5 microseconds. He has completed its task in 200 milliseconds. And I think, I don't know, I just think that Forth and analog computers might be a match made in heaven for modern hybrid computer systems. I'm here not speaking in any official role of my startup company. My colleagues have no idea that Forth even exists, which is a pity, but I can't change this. They are all much younger than me, and they missed the great opportunity to play with Forth on small machines in the 80s. But nevertheless, it would be really interesting, I think, if we maybe could set up an interest group or just meet for a brainstorming Zoom session to think about what would be needed to seamlessly integrate a hybrid computer, an analog computer as a co-processor in a Forth environment. And since we talked about space requirements, interestingly, we had some discussions with the Colorado School of Mines. And they have a think tank project where they think about mining on the moon. Of course, what would you do else on the moon? And the main problem in such an environment, apart from mechanical issues caused by regolith, is ionizing radiation. And most of our current high-density CPUs is just not suited for these environments. Imagine the results of a bit flip. Someone mentioned Ariane 5 rocket with the overflow problem, which caused the complete mission to be a full loss. In an analog computer, if a charged particle hits some of your electronics, basically, who cares? You get a little bit more noise, but the integrations basically get rid of this noise. So analog computers are incredibly resistant to ionizing radiation. And that makes them very interesting for embedded applications and also aerospace applications. And this too would be a match made in heaven if we could manage somehow to come up with a hybrid controller that's basically a microcontroller that is attached to the analog computer. In the case of the reconfigurable system I showed you, we use a TeamZ microcontroller. So it's an ARM processor with lots of memory and high clock frequency, really powerful thing, and have a really seamless integration of analog computers as co-processors in a Forth environment for example, industrial purposes, for aerospace applications. even for medical applications. Medical applications are also very well suited for analog computers due to the requirement of high energy efficiency. And using modern analog computing technology, don't think that this is modern. Okay, that is a new analog computer, but the design is very classic. I don't talk about patch cables in modern analog computers. Everything will be software defined, but everything will still compute with variables represented as voltages or currents. And in the medical environment, for example, if you imagine a heart pacemaker, brain pacemaker, a control circuit for an insulin pump, these are all existing nowadays, but they need power, lots of power. You have to charge them or you have to swap batteries, which is really horrible. And using modern analog technology, it is really feasible to implement systems that can basically live by energy harvesting from within the patient's body. But this won't work if you need a hybrid setup with some power-hungry C-programmed monster MCU. This would also require very efficient and very lightweight digital parts to, for example, configure the analog computer to read out data, to connect to medical equipment in the hospital or at the doctor's office. So I really think Forth and analog computers could be a match made in heaven. And that is basically all I would wanted to tell you today. Thank you very much for your interest and for your audience.
Fantastic, Bernd. Love it.
Thank you very much.
Thank you very much.
Are there any questions for Bernd?
Yes, I do have a question.
Go ahead.
What do analog computers solve? Do they solve systems of differential equations, and how sensible are they to variations in temperature or component tolerance specifications?
That's a very good question. You are right in all points and with all your questions. Basically, traditional analog computers required very high precision components, high precision resistors, special capacitors with negligible dielectric absorption. What we do when we need a high precision solution, we perform a calibration run. So we can basically live with low precision components, and temperature drift is not a problem in our case since the solution times are so incredibly quick. Even with our discretely built analog computers, typical computation times are well below a millisecond. So temperature variations don't play a role at these short time frames. When it comes to systems of coupled differential equations, depending on the problem you have, they are not very they are not highly influenced by these little aberrations. For example, I did some work recently on the oscillators in your heart, the sinus node and the atrioventricular knoten, and I don't know the English word, only the German ones. And interestingly, these can be, for example, described by coupled differential equations, and they have implicit amplitude stabilization. So for many problems, you don't need high precision and high stability. There are cases where you need high precision, which is not directly attainable by an analog computer, but there are two approaches to solve this problem. The first is you could use the analog computer to basically guesstimate a rather good solution in very short time and then improve on this solution with clever numeric schemes. Or you could even reconfigure the analog computer on the fly after it has yielded the first approximation to a solution, and then use the very same computer with different scaling to produce a correction and produce a correction for the correction. We have demonstrated this for a really perverse task, solving systems of linear equations, which are not well suited for analog computers, but we had a prospective customer who was very interested in the question, is it possible? And the answer is yes. And we can achieve arbitrary precision, but we need an analog computer coupled to a digital computer. We need some tit for tat game between these computers going on. So the analog computer yields a solution, the digital computer reconfigures the analog computer, which computes a correction, and so on and so forth.
And then is the speed still better than Gaussian elimination in an all digital computer?
Not at the moment. It was merely a proof of concept. The performance was abysmal, to say the least. But that was mainly due to several factors. The first factor is most of the systems we have nowadays are still built from discrete components. Our bandwidth is around 1 megahertz, so the highest frequency component in your solution can be 1 megahertz. So we have solution times in the range between 10 and several hundred microseconds typically. And the second reason is, since it only was a proof of concept, don't laugh at me, but the connection between the hybrid controller and the digital computer was done by USB. And the USB performance basically killed everything. It was way, way, way too slow, but it really was only intended as a proof of concept.
Okay.
So you do have some sort of a self-calibration process.
Yes.
Great.
Basically quite straightforward. If you think about error sources in analog computers, you have drift and you have linearity problems. Drift can be measured before a computation starts, and you can correct the drift by injecting accordingly some bias currents. And the linearity errors can be counteracted by changing the coefficients at all inputs of a computing element. And the calibration procedure is really quick. And typically, you don't need to do a calibration before every computation, but maybe every hour or the like, when your environmental conditions change rapidly with respect to temperature, for example.
Bernd, we have a question from Atle. Atle, go ahead.
No, I'm just wondering about, at the beginning, we saw this switchboard that you had in order to configure it, and now you're doing it electronically. Are those digital electronics? Are those registers that we can set high or low, or how does that work? That would be the way to connect forth. It would be to connect it to these registers.
Yes and no. The actual switches are analog switches. So these are bidirectional switches which allow variable voltages and or currents to pass through, but controlled. These switches are controlled by, of course, individual bits which are shifted into a shift register. So we have analog switches, switch matrices in a hierarchical structure. Basically, you can't do an all-to-all connection. For example, if you aim for 1,000 computing elements, you would end up with millions of switches. That is even impractical on a single integrated circuit. So we have a rather clever and honestly patent pending at the moment, hierarchical structure for our interconnects. But the interconnect switches are either on or off. Followed each row of switches, each column of switches is followed by a multiplying digital analog converter. So you can introduce weights into your computation. But these, of course, also accept digital values. So the programming, it's really, really software defined. What you send to the analog computer is at the moment a large JSON message with basically several kilobytes of configuration data.
Oh, Jason.
Okay, thank you.
I had a quick question.
Go ahead.
I know several years ago, or many years ago, ARM designed an analog computer. And I think some of the challenges they had back then was that the silicon design tools were not really available for analog design. And do you guys think you'll run into the same problems, or?
There are development tools for analog integrated circuits, but they are vastly different from the digital development tools. We had quite interesting talks with Intel and the Intel Ignite program, and Intel also was interested in pursuing analog computing. But the problem is when your company is centered around digital integrated circuits, basically analog is just black magic. It's not even white magic. It's really black magic. We are an inherently analog electronic company. So for us, digital is the outlier, so to speak. There are two main tools, Synopsys or Cadence. And Cadence is basically the tool to go for if you want to develop analog electronics in CMOS technology.
Okay, thank you.
Right.
So thank you very, very much for your interest. And I'm looking forward for the next talk.
Bernd, it's a great pleasure to have you in the meeting. We always learn about new sophisticated uses of analog computer in the 2024 and
Thank
next in
for
the 2025.
Thank you very, very much. It was a pleasure.
Oh,